Hello and welcome back to Let's Code Physics. I am excited today to continue on with our Drude model circuit. Today we're going to be looking at circuit branches that run in parallel to each other. So what I've got here is I've got sort of our main branch here. It's got the largest voltage or the largest electric field. As you can see from the large arrow in the middle, so I've added a little graphic to help us visualize the electric field in each of these. So each of these arrows that you see in the wires, they represent the magnitude and direction of the electric field. So this indicates the electric field is pointing this way, well, actually the electric field is pointing opposite of that way because the electrons are supposed to go against the electric field. But point being, this is the direction the electrons go, and the length represents the magnitude of the electric field. So we're operating under the assumption of positive charge carriers here, which is the direction that current goes. So that's all right. We have smaller arrows over here and over here because we've got less of an electric field in each of those. And then of course we have the current and the electric field splitting up here. So these are actually technically two wires. I haven't made them different colors yet, but you can see they have some overlap up here. This is just so that you can visualize the yellow as the top and the cyan as the bottom. So what I want to do today is I want to review with you how I set this up, give you an idea of how we got the electric field for each of these things, and then we're going to fix a problem that we have. You can probably already see it, but I'll leave you in a little bit of suspense by not identifying what that problem is. So the first thing that we added was this arrow that we have here. So this just points again with the magnitude and the direction of the electric field. It's scaled by a factor of 5 because that seemed to work well for the visuals. Let's see. Instantiate electrons this wire. I already did that. Good. Sorry, usually the triple hash mark means it's something that I need to talk about, but I seem to have forgotten to remove those from my last recording. So what we've got here is we've got, how many wires do we end up with? 1, 2, 3, 4, 5, 6, 7. We've got 7 wire objects. We've got the one on the left, that's the one in red, so that guy is sitting over here. He gets a quarter of the battery voltage. The two on the top, so one points to the right and one points to the left. So again, that's so that we can get current going to the right here and current going to the left here. They each get 1/8 of the battery voltage. And then down here we get, let's see, this is the right resistor. So this is the one in blue. And it's symmetric to the one across from here, so it gets a quarter of the battery voltage. And then these two are symmetric from the top, and so they get 1/8 of the battery voltage. And then the middle branch is where we're saying that the battery is located. It's kind of an artificial thing because the battery is not an object in this model. So we've got So we've got a resistance in here that's taking up half the battery voltage. So let's take a look at where those values come from. So the way we have the circuit set up is that we have a middle branch, and then we go around to the right. Meanwhile, we also have a branch that goes around to the left. Now, in order for the code to work, I've got to model each of these wires with a resistance. I've tried out having 0 resistance wires. It simply doesn't work. So we give each of these folks a resistor. Those are my highly technical resistor drawings. And since these wires, the ones they're going vertically, are twice as long as the others, we're going to give them a resistance R. But then these horizontal going wires, they're half as long as these are, so we're going to give them resistance R over 2. R over 2, R over 2, R over 2. Now, of course, we can't get anywhere in a circuit without a battery, so we're going to model the battery as being right here in the middle. And we're just going to call that thing's voltage B for battery. I usually call it VB, but that's getting more and more cumbersome to write. So what we do here is we start to think about the currents that are going to flow in these circuits. So current, by convention, flows out of the positive end of the battery into the negative end. So when I think about this loop, I can think about it as having a current of I. I can think about this one as having a current of I. But what that means is when those two currents meet here at this junction, that those two currents need to add, so that the current that I get in this middle branch is 2I. Alright, so you've got a current I flowing in here, a current I flowing in here. They're going to join forces, form a 2I here. Then at this junction, it'll split up. It'll go I and I. We know that these are going to be equal because the circuit is left-right symmetric. So there's no difference between the left side and the right side. So those two currents should be the same. So the next thing we do is we apply the loop rule. So we just go around each loop. Let's just take the right loop, for example. And what we do is we keep track of all the voltage gains and losses around the loop. So if we start, for example, right here and go around, I guess that's clockwise, we start out by gaining a voltage B. So we start out by gaining a voltage B. Then we hit this resistor and we lose a voltage 2IR. So you just take the current times the resistance, so the current is 2I, the resistance is R. Then we keep coming around here and we lose R over 2 times I, so I get an IR over 2. I hit this one and I lose an IR, again current times resistance. Here I lose one more IR over 2, and that all has to equal 0. It's basically conservation of energy for a circuit. So what I can do is I can group all of these things together. They've all got an IR. So I've got a, let's say it's minus. So I've got a 2. I've got a 1, so that gives me, I got a 1 here, so that gives me 3. And then these two combine to another 1, so that gives me a total of 4. So I get a total of 4 IR equals 0. So what that means, since I can specify the resistance in these, in the code, I want to solve for the current. So the current in the right branch and in the left branch is supposed to be the battery voltage divided by, that's going to be 4 times R. Cool. Now what I need to be able to specify in the code is the voltage that each of these resistors eats up. So what I need to do for each of these is I need to take the appropriate current and multiply it by the appropriate resistance. So for example, in this branch, the current is going to be B over 4R, the thing we just calculated. But in this branch, the middle one, the current is going to be B over 2R. Ooh, my handwriting is getting worse as the video goes on. B over 2R, since it's twice that, it's going to reduce this 4 to a 2. So when I want to get the voltage of each of these, I just multiply them by the current. So I just take the resistance times the current. So for example, if I take this resistance times the current, these two R's will cancel out, and the voltage I'll get is B divided by 2. Then if I take this current and multiply it by this resistance, I've got a 1 over 8. So my R's will cancel, and I'll have a B over 8. Here, the R's will cancel, I'll have a B over 4. Here, the R's will cancel, and I'll have a B over 8, just like I had before. And then this branch works out the same way. Because it's metric, it's going to have the same math going on for the loop rule. So this thing's going to get a voltage of B over 8. This one gets a B over 4, and this one gets a B over 8. I hope my color coding is compensating for the crowding. Let's double check and make sure that's what I put in. So let's see, we've got our left resistor, the one in red. Over here we've got our one in red, so that according to this is supposed to have B over 4. So my red and my blue should both have a quarter of the battery voltage, and lo and behold they do. A red one and a blue one have a quarter. Cool. My top and bottom wires are supposed to get an eighth of the battery voltage. There's an eighth. There's an eighth, there's an eighth, there's an eighth. That way, and you can think of those as adding up to a quarter because they're each half the length of the other ones. And then finally, the middle one with the battery is supposed to get half the battery voltage, and there we go. Now you notice we don't yet have a way to model the actual battery. If I could actually just model the battery in the middle here, I wouldn't need to manually set up the voltage for each of these. I could have the computer figure out what the voltage is going to be. But I haven't figured out how to do that yet. If you have any suggestions, let me know. And so the red and blue currents are supposed to be equal. This one's supposed to be about twice of each of those, and these are each supposed to be about half of the red and blue currents. But if you look, that's not really what's going on here. The red one definitely has more charges passing through it than the blue one. You can just look at the number of charges in it. So you imagine your current meter is set in the middle of each of these wires. This one's definitely got more current going through it than this one does. And in fact, if I graph the current, my red and my blue are drastically different, right? So it's a difference of 5 compared with 20, and that is not okay. You know, if it were 18 and 20, I would say, oh, okay, you know, it's just a computer error. So I was looking over this while getting ready for this video, and I think I have figured out where the problem is. The only thing that's different about red versus blue here is that red is being created first. And in fact, if you move those, I'm not going to go through it since it takes a while for the graphs to generate. But if you swap these two, then that flips. Then the blue one gets more current than the red one. So there's some problem with the red one having priority in the order in wire list. And the reason that is, I'm pretty sure, is this line up here. And this is what I want to spend the rest of our video fixing, is that the way that the electrons hop from one wire to another is the electron. So we're looping over the electrons, and then we start looping over the wires, and we say if the electron is in another wire, meaning if it meets the geometry conditions for being inside another wire, then place the electron in that other wire. But what that means is that there's priority given to the given to wires based on their order. So an electron in that can jump to the first wire has priority over the electron that can jump into the second wire. Or I guess I should say, if the electron can jump into either wire, it's going to jump into it'll jump into the later one. Oh, that's right. It's not the problem with red versus blue. It's the problem with these two wires in the top. So the one going right is getting more than one going left. Sorry, I got myself confused there. So basically, if I swap these two, then it'll have a left preference over a right preference. Or excuse me, it'll have a right preference over a left preference. Yeah. So it's the wires that are created later in the list have priority over the wires that are created earlier in the list because they occur later in this loop. And so that means that it's jumping to one of the wires, but then it's jumping to the other wire. And so it's very rare for the electrons to end up in an earlier wire. So what we need to do is we need to change this to a probability. We need to randomly assign the electrons to a wire. So here's the way I'm thinking about doing this. We're going to create a list. We're going to create a list, wires I could jump to. And so this is going to be a list of all the wires that it's possible for this electron to jump to. All the wires that this electron is technically within the coordinates of. So obviously its current wire is fine for that. So we're going to have, let's see, where do I have the, I guess we'll just have this be the numbers of the wire. So this is going to be num. So we'll start out with the current wire that it's in. And now instead of placing the electron in that wire, we're going to add to that list. So we're going to do wires plural I could jump to. We're going to append the wire that we're currently considering. Oh, that's right. It's W is the wire. Okay, because I think it would be better to keep track of the wires rather than their numbers. So let's just go with W there, and then we'll go WP here. There we go. But we're not going to set that anymore. Cool. So now we have a list of all the wires that the electron could jump to. So now what we need is a random number. Let's see, the way you get a uniformly distributed random number is this uniform here. So let's do this. Let's say wire, actually let's call it new wire number equals, let's make it a uniform, and I think the easiest way to do this is going to be to go from 0 to the length of wires I could jump to. I guess I should call that wires to which I should jump, but I've already written it a couple times. So what this is going to do, so like, let's say that there are 3 wires that it could jump to. This is going to pick a random number between 0 and 3. So what we're going to do is we're going to take that number and we're going to round it down. So for example, if we had 3 wires it could jump to, it's going to go from 0 to 3. But what that means when we round it down is that we're going to get a number that's 0, 1, or 2. So what we're going to do is we're going to say new wire number. Actually, I guess I don't have to do that. I can just do that here. We're going to take this and we're going to turn this into an int. So in other words, we're going to take this random number we get and we're going to truncate it down to an integer. And technically there is a probability that it could select the length, which is not going to be accessible in the list. So let's make that length minus 0.00000, a whole bunch of zeros, 1, just so that way if there are 3 wires, it's not going to try to select 3, and then when we try to access 3 off this list, it won't be able to find it. So then what we can do is we can say electron.inWire is equal to, I just need to get wires I could jump to. Oops. Not what I meant to do. Wires I could jump to. Copy, not paste. There we go. Wires I could jump to, and then I need element new wire number. There we go. So I've got my electron in wire, and electron.inWire is, oh, that is a number. Okay. So actually I don't want this list just yet. So now I need to change, let's see, do I need to change the W value? I think I probably do, just in case I reference it below. So W is going to equal wire list, that is how you write it, right? Wire underscore list of electron.in underscore wire. Cool. So what we're doing is we're selecting a random wire from all the wires that the electron could be in, and then we're assigning the electron to that wire, because this e.inWire is the label, is the index of that wire in wire list. Awesome, awesome. I think that will tidy that up. So I'm gonna run the code, and we're gonna let it run for a little bit, and we're gonna see whether that fixes our issue. I don't see any error messages, so I think I'm on the right track. So, oh my, oh bother. My circuit is literally falling apart before my eyes. Let's see what's going on with that. Let's see. We've got if e.particle.pos.x is less than the right. So if it's less than the right, if greater than the left, if it's less than the top, greater than the bottom. Oh, you know what? I have not checked the z coordinate for these things yet. Am I randomizing these in the z direction? No, these are all randomized in just the x and y direction, so I don't need to worry about their y and z. What is going on with this? Let's take a look. So I've got some falling out here. That is bizarre. Wow, wow, wow. Oh, you know what? I've referenced the wrong index here. Oh yeah, I have totally referenced the wrong index here. Okay, I see my problem. The problem is that new wire number, that's the number from the list of where they're getting stored there. So actually, I want to store here. Actually, I do want to store that wire number. I want to store wp.num. Right. Okay. Here's what I needed to do. Sorry. Here's what I needed to do. I'm referencing the wrong index. I need to store wp.num in this list. So then my new wire number is this thing, and then my e.nwire is new wire number of wires. Actually, this needs to be wires I could jump to of new wire number. There we go. Because this. Yeah. Okay. Yeah. Now this is going to store the number of the possible wires I could jump to. So when I select a new wire number, it's going to be, this is now that number in that list. So my naming threw me off. New wire selection. So that this wires I could jump to of new wire selection is the new number for us. Okay, let's try that again. Oh, and now I get an error. Hooray. Wire instances no attribute num. I thought we had .num earlier. Oh, whoops, it spelled out number. There we go. That ought to fix that. Of course it doesn't. What else is going wrong? Object cannot be interpreted as an index. Oh, right. E.nwire is that. All right, so I need E.nwire is... all right, I need one last thing. I need wire list of this. Okay, cool. So we've got wire list. Okay, E.nwire is the number. Right. Okay. There we go. No. E.nwire is the number. Let's see here. Wires I could jump to .append. wp.number. Wire list of E.nwire. Alright, let's go back here. What am I looking at here? W equals wire list. Object cannot be interpreted as an index. E.nwire. I guess right here, print for me please, E.n_wire. On F5, it'll throw me an error, but not before telling me what happened. Oh, when did n.e, what? Okay, E.nwire here is an index, right? Yes. So where does E.nwire? Yeah, that's definitely a number there. Let's go back up to the class electron. Let's see. N.wire. Yeah, N.wire is a number. So where is N_wire? When does that become an object? Wire list. Num equals E.n_wire. Wires I could jump to .append WP number. Oh! It might be because this thing is a float. Let's try print new wire selection. Let's go F5. All right. So this is the new one selected, right? So that's the print statement is new wire selection is 0. So then I've got E.nwire equals wires I could jump to. Oh! It's the problem is trying to select 0, and the first one I have here is a wire, so I need W.number. That should be the last thing that I need to fix. I've got everything consistent now, I believe. And my code is running, hooray. And my electrons are not falling out of the circuit. That's never a good thing to have in lab. Can't do much circuit lab with wires with electrons falling out of your wire. So I'm going to let this run for a little bit in fast motion, and then we'll take a look at it and conclude. All right, we're back, and you can tell just from the visual here that our red and blue wires are more symmetric than they were before in terms of the electron flow. If we take a look at the current graph, meaning the graph of the current, it's also the current graph of the current. Red and blue currents are pretty much the same. There's a little bit difference. I mean, we've come to expect that. They're converging a little bit here, so I'd expect them to, for blue to be more than red a little bit, for red to be more than blue a little bit, since we do not have a billions and billions of electrons to average over like we do in a real circuit. And then we've got, did I say billions and billions? It's definitely more than that. I mean, Avogadro's number, The one thing I'm not terribly certain of, I was watching it also last time, that there's this kind of like backlog of electrons here in the bottom corners that I don't see quite as much here in the top corner. So that would be something else to investigate. But we've got the currents working out better. In fact, the current in the exterior branches is right around 10. Current in the middle branch is around 20. So just like Kirchhoff's law predicted, we would get about half the current here that we got in the central branch. So that is pretty cool. So this has been a really fun and interesting series. I think it's been helpful to visualize, how, electrons under the influence of electric fields make a circuit work. I mean, we've been able to get series and parallel circuits now. We were able to get an RC circuit. But I think for right now, I'm going to put this series on hold because I'm not sure where to go with this code from here. What I had originally hoped to do was to be able to set up a battery object and then have that determine the way the electrons flow around the circuit. And I just said, I just need to look up how to calculate the electric field in a wire, based on what's going on, at the beginning of it. It turns out that's not really something we know how to do, at least according to Griffiths. That's not something we know how to do. So I'm going to have to do some more thinking on this. I'd be glad to take some suggestions on it. But for right now, we're going to call this series to a close. For the rest of Season 4, we're going to pick back up with our projectile motion, and I've got something a little fun planned that I think will be coming up next week. I'm not sure. I'll have to double check the schedule, but we'll take a little bit of a break from the serious physics stuff to do something a little fun just in time for spring break. So thank you so much for watching. Have a wonderful day. I will see you next time. Bye-bye.